All right, so we continue with multiple access protocols. So there are two types of links, point-to-point. So this is point-to-point link between Ethernet switch host. So there's a protocol called point-to-point protocol for dial-up access. Broadcast, shared wire or medium. So broadcast is somewhat important for us because if it is broadcast, then people who the data is not intended for can listen to this communication. So this has happened in old-fashioned Ethernet if you connect the devices with hubs and so on. So in that scenario, you can listen to every communication, like using Wireshark in the listening mode. Or upstream HFC in cable-based access network, or similarly, wireless LAN standards or 4G or 5G satellite communication. There's a typo here. It should be 5G or 4.5G and so on. So multiple access protocols, single shared broadcast channel, two or more simultaneous transmission by nodes, interference. So the idea is this: so if you're sharing the medium and you try to transmit at the same time, this would cause a collision, right? Because only one can use that medium. So collision if node receives two or more signals at the same time. Multiple access protocol, distributed algorithm that determines how nodes share channel. In other words, determine when node can transmit. Okay. Communication about channel sharing must use channel itself, no out-of-band channel for coordination. So as you can see, there is a problem. Assume that it is like in the old cases where you're using a hub and 8 computers are connected to that hub using an Ethernet cable. So if there's a broadcast protocol here, then when a computer sends data, it is transmitted to every node. So this means that you are using the channel. So when another computer wants to send data, the channel will be busy. So if they try to transmit, there will be collisions. So this would actually cause communication problems. So they have to transmit when they are allowed to. So this is the topic in multiple access protocols, okay? So an ideal multiple access protocol will be something like this. Given multiple access channel, MAC of rate R bits per second. So desired data is as follows. When one node wants to transmit, it can send at rate R. So this means that they can use the maximum capacity of the channel. But when M nodes want to transmit, each can send at average rate of R divided by M. So this is what we desire. And we also want fully decentralization, no special node to coordinate transmissions, no synchronization of clocks, slots, and it should be simple. So as you can see, this is desired, but it's hard to obtain. So in MAC protocols, there are 3 broad classes: channel partitioning, divide channel into smaller pieces, time slots, frequency, code, etc. Allocate piece of node for exclusive use. So this is actually what we talk about FDM and TDM. Similar thing applies here. Random access, channel not divided. It allows collisions, but when collision occurs, they wait for a random time and then use the channel. So this way they recover from collisions. Taking turns, not take turns, but nodes with more to send can take longer turns, etc. So here you need some kind of a synchronization. So let's look at channel partitioning MAC protocols, time division, multiple access. Access the channel in rounds. So you divide the channel into time. Each station gets fixed length slots. General length equals the packet transmission time in each round. Unused slots go idle. So this is something undesired, right? Because here one wants to send data. So it has to wait another slot to use the second part of it. So unused slots go idle. Example, 6 station LAN, 1, 3, 4 have packets to send. Slots 2, 5, 6 are idle. So as you can see here, you cannot use the maximum capacity of the channel where you could do. So we talk about FDMI, frequency division multiple access, channel spectrum divided into frequency bands, each station assigned fixed frequency band, unused transmission time in frequency bands go idle. The same example goes here, like 1, 3, and 4 have data to send, but others doesn't have anything to send. So random access protocols have some advantages, but also disadvantages. When node has packet to send, transmit at full channel data rate R. So no a priori coordination among nodes. But if by chance two nodes want to transmit at the same time, this would cause a collision. So random access MAC protocol specifies how to detect collisions, how to recover from collisions, for example, via delayed retransmission. Examples of random access MAC protocols, Aloha, Slotted Aloha. So these are the traditional oldest ones. So I'm not going to go into detail, but I will go talk about CSMA /CD because it is used in Ethernet protocol. So let's move on to carrier sense multiple access. Simple CSMA, listen before transmit. If channel sense idle, transmit the entire frame. If channel sense busy, defer transmission. So human analogy, you don't interrupt others. So CSMA with collision detection, collisions detected within short time. Colliding transmissions aborted, reducing channel wastage. Collision detection easy in wired, difficult with wires. Okay. So collisions can still occur with carrier sensing. Propagation delay means two nodes may not hear each other just started transmission. So example is this. So at time t0, this one starts transmission, but the others haven't heard it yet. So they think that the channel is idle. So they also start transmitting. So at this point, you have a collision. So entire packet transmission time wasted. Distance and propagation delay play a role in determining collision probability. So CSMA/CS reduces the amount of time wasted in collisions. Transmission aborted on collision detection. So Ethernet uses this algorithm actually, CSMA/ collision detection. NIC receives datagram from network layer, creates frame. NIC senses channel. If idle, start frame transmission. If busy, wait until channel is idle, then retransmit. If NIC transmits entire frame without collision, NIC is done with the frame, right? If NIC detects another transmission while sending, abort, send jam signal. After aborting, NIC enters binary exponential backoff. So this means that after AMP collision, NIC chooses K at a random from 0 to 2 to the n-1. NIC waits K times 512 bit times and return to step 2. So when there's a collision, this means that you randomly select a number. Initially, between a small amount, but if you observe more collisions, the random number you choose actually is from a larger set. So this way you try to avoid collisions. But if there are more collisions, you have to wait longer. That is the idea. So there's a formula here, actually measures the efficiency. So it measures actually, how good is it. So I'm not going into detail about this formula because how you calculate it is actually a long process, by the way. But the idea is that you can play with these parameters to have better efficiency. So channel partitioning MAC protocols share channel efficiently and fairly at high load, inefficient at low load, delay in channel access, 1/n bandwidth allocated even if only one active node. So as you can see, it has advantages but disadvantages. Random access MAC protocols efficient at low load, single node can fully utilize channel, high load, collision overhead. Taking turns protocols look for best of both worlds. So idea is to obtain the good parts of this too. So in this case, we can talk about polling. Controller node, so here there's a controller here, unlike the others, invites other nodes clients to transmit in turn, typically used with dumb devices. Concerns polling overheads, latency, and single point of failure. So if this device is somehow broken, you lose the whole communication. Token passing, in this scenario, you don't have a controller. Control token pass from one node to next sequentially. Token message concerns token overhead, latency, and single point of failure. Again, somebody might stop sending the token, right? Like this. nothing to send. And this has data, so they send the data, then pass the token and so on. So strangely, cable access networks uses all these three, okay, FDM, TDM, and random access. So in this case, internet frames, TV channel control transmitted downstream at different frequencies from CMTS, cable modem termination system. So multiple downstream broadcast FDM channels up to 1.6 gigabits per second per channel. Single CMTS transmit into channels. For the upstream, multiple upstream channels up to 1 gigabits per second per channel. Multiple access, all users content, random access for certain upstream channel time slots, other assigned TDM. So as you can see, all of these methods are used in practice. There's also another protocol called DOCSIS, Data over Cable Service Interface Specification. FDM over upstream, downstream frequency channels, TDM upstream, some slots assigned, some have contention. Downstream map frame, assign upstream slots. So there's a protocol here called, you send map frames to check if you have an empty slot and then you use it. So request for upstream slots and data transmitted random access binary backoff in selected slots. So as you can see, all of these topics we talk about actually used in practice. So here you ask for you send map frame for an interval T1 between T2. So mini slots containing mini slots request frames and assign mini slots containing cable modem upstream data frames here. So summary of these MAC protocols, channel partitioning by time, frequency, or code, like time division, frequency division. Random access, there are many protocols. As I mentioned, CSMA with collision detection used in Ethernet and CA used in Wi-Fi. Taking turns used again in practice like in Bluetooth and so on.